Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Zeng, who will tell us about error structure tailored fault tolerance and early fault tolerant quantum computing. So Zeng is currently a tenure track associate professor at the Institute of Natural Science, Shanghai Jiao University. Prior to this, he was a postdoc at the University of Chicago from 2021 to 25, and a visiting scholar at USTC. And he completed a PhD and bachelor's degree at Tsinghua University and Nanjing University, respectively. He also serves as an editor of the journal Quantum. Yeah, so Pei, the floor is yours.
Okay. Thanks, Jiao, for your introduction. So today, actually, I want to make this talk quite casual, so you can interrupt me at any time if you want to ask any questions. So this work is actually done during my postdoc at the University of Chicago. Actually, I spent 1.5 years sometimes to fully finish this work, but so we change our research contents a lot from our initial motivation. But yeah, today I will just tell you our final results. But yeah, if you want to know more, I can also tell you more about the motivations. And okay, so the title of the talk is called Error Structure Tailored for Tolerance and Early Photon Quantum Computing. But basically the first terminology is invented by us, to capture some technical contents, technical issues in our work. And so let's just begin. I just don't want to waste too much time. So about for Torrent quantum computing, we are talking about quantum error correction. So where are we at this moment? So we know for Google's Willow chip, we can achieve a logical error below the physical error rate, in actually last year's a demonstration. And I've recently know they also make this logical error even lower because they improve the signal gates. So basically we can expect when we increase the distance of the surface code, the logical error rate will decrease exponentially in the following years, making the error corrected device possible in the near term demonstration. And on the other hand, say neutral in the neutral atom platforms, to kill error, these companies they also demonstrate similar surface code scaling behavior. But of course, at this moment, the error because the physical error in the neutral atom platform is still high at this moment. So they can show this kind of scaling, exponential decrease, a logical error scaling, but still the error is quite large at this moment. So I think at least for comparing the error rate, the superconducting device still performs the best at this moment. But I think this neutral atom platform will also become it's also very competitive in the near term. But we can see there's a rapid progress on quantum error correction. But the thing is if we I also work on something about quantum algorithm. So I formally check some resource estimation of a useful quantum algorithm. So I checked 3 very typical quantum algorithm. The first one is the trotter-based quantum simulation of the Heisenberg Hamiltonian. And the second one is the quantum signal processing of the FEMA ground state energy estimation. And the third one is the Schwarz algorithm for the RSA 2048. So these 3 types of algorithms so it's what people believe, and which is the most useful aspects of the quantum algorithms, which is to perform the dynamical evolution, to perform the ground state energy estimation, and also do the cryptography. But if you check their resource cost, you can find like the estimation in this paper is still like they still need a lot of like T gates or Toffee gates, and also it requires like still like a large number of logical qubits. So if you take the resource cost of each like T gate into account, because for each T gate you need to do like magic state distillation. Of course, originally we'll also have cultivation, but if you consider the magic distillation, you can see like if you want to do a logical T gate, you still require a lot of like physical gates. So take all this resource into consideration. You will see like if you want to perform like a useful quantum algorithm, you will need like at least 10 to the 10 gates and like 10,000 physical qubits. So this is still like quite like a scaring, and seems too hard to achieve in the near term. So so one of my research focus formally is on like to reduce the cost of this kind of like a quantum algorithms. So recently people have some like a design of early fault-tolerant quantum algorithms. So these quantum algorithms, the motivation is try to like reduce the cost of this like T gates or Toffee gates, and try to use
Uh,
some like
I just
uh
wanted to interrupt briefly.
uh-huh
Because I just don't have any intuition.
uh-huh
Like what would be the practical thing that you can do? Like how many T gates is practical at the moment?
one.
Oh, okay. I
Okay,
see.
so yeah,
Like
if you
if
check the archive paper like maybe yesterday or the day
Mm,
before yesterday, so Google have like published a paper. It's called like which is like demonstrate their magic state cultivation, like
mhm,
a like a design. So they have shown like you can prepare a T gate, logical T gate,
mhm.
with like a infidelity of 10 to the minus 4, so which is
Okay.
not too. So of course, if you want to do like 10 to the 8 T gate,
Yeah,
so
yeah.
you need to ensure like each T gate is 10 to the minus 8, but we still
Yeah.
don't have it at this moment.
Okay, I see. I see. Okay, thank you.
Yeah. So also like for the Q era, this platform, they also demonstrate like the magic state distillation. Like I don't remember, it's like 15 to 1 or like a some like 7 to 1 quite type of like a distillation, but the error rate is very high. If I remember correctly, it's several percent. That is like not useful at all at this moment. Okay. Okay. Do you have any other questions?
Oh, no. It's fine.
Okay,
Yeah.
okay,
Thank you very much.
I
Yeah.
will go. I will move on, and
Hmm.
yeah, just interrupt me at any
Hmm.
time. Okay, okay. So formally, just like to people, uh, I formally work on like this quantum algorithms, and I'm trying to reduce this gate count so that we can make like the resource requirements for use quantum application lower. But when I do this like so this early photon quantum algorithms designs can be used to like reduce the gate count in this like a high precision phase estimations, which is usually for like a ground state energy estimation, and also like Hamiltonian simulation. So which is for like the like to check like the properties of like a dynamical evolution of a Hamiltonian system, and also some other like a variation algorithms like QAOA. They can also like which is empirical, of course, but they can also like reduce the gate count remarkably. So literally, you can have like many types of like early photonic algorithms, but their major spirit is to save the budget, which is like to reduce the gate cost. So like for example, in our paper, this PRX quantum paper, we have shown like to comparing to the traditional trotter, like a rigorous trotter bounds, we have shown like we can reduce like the T gate counts like for like 2 orders of magnitude for some special case. So basically you can introduce some like random sampling or some empirical like a design so that you can save the like a budgets, base budgets for the quantum algorithms. But the thing I want to emphasize is that for all these early photon quantum algorithms, they all have the similar architectures, which is based on the Clifford J5, this kind of like a gate design. So what I mean by Clifford J5 plus 5 is like first you first decompose the whole quantum circuit to Clifford gates. like a C0, Harman, and S case, with some like extra like a zero rotation gates, with like a where the zero rotation the phi angle is determined by some classical input of the classical algorithm of the classical parameters of the quantum algorithms. For example, if you want to do like a Hamiltonian simulation, so the phi angle is determined by the Hamiltonian interaction parameters, like the like let's see like the Heisenberg Hamiltonian. You have like the jumps and the yeah. I don't know whether I need to explain too much, but the thing is like people usually embed the classical information of the which you want to make as the input of the algorithm to the phi angle of the gates. So you use the phi angles to encode the classical information so that you can efficiently embed the classical inputs to the quantum circuits. So basically like for our just like for example in our paper we have this like a shorter LCU based Hamiltonian simulation, and in this circuit you have some like a shorter segments. So in each shorter segments you have many CNOTs and some rotation gates. So this is like a Clifford plus 5 like a architecture. So when you do this kind of Clifford plus 5 architectures, the major resource count will be take from this like a phi rotation. So this phi rotation for the shorter circuits, it's usually with a phi angle which is small, like a 10 to the minus 2 or 10 to the minus 3. But for like some variational circuits, the phi angle can be arbitrary. You can set the phi angle to arbitrary rotation. So, but if you check like the resource count for this logical rotation gates, this will be like very costly. So, usually the way people like to implement this like a rotation gates, logical rotation gates, is to first compile this logical rotation phi gates to many T gates by some like a Solovay Kitai like a gate compiling methods. So to the state of the art compiling methods to compile the rotation gates to T gates usually will cost you like a 40 T gates. Like if you have some like ancillary qubits, if you don't have any ancillary qubits, it will cost you like 80 to or even 100 T gates to compile this like a zero rotation gates. Okay, and for each T gates, as I have mentioned, this if you use the traditional like a distillation methods, you will introduce like a extra like a d to the 3 like a space-time cost. So usually like one rotation gate will take you like a at least 100, sometimes 1,000 space-time cost comparing to our CNOT gates in the fault-tolerant circuit. So which is like a quite like a it's like a dominant like a limiting factor. It's a bottleneck of the realizing this like a fault-tolerant quantum computing. So the motivation of our work, like in this talk, is try to like reduce the cost of this like a rotation gates. So I will show you. So the major spirit is to follow this paper by this by the group of Kensuke Fuji from Osaka University. So in 2024, they proposed like an architecture, a hybrid architecture called the star architecture. So in this architecture, so they proposed a partial fault-tolerance design. So the major idea is that you do this like a Clifford gate based on lattice surgery, based on the transversal gate or lattice surgery. So this can be done with like a very efficiently with a low space-time cost and a very high accuracy. And you do this like a analog rotation gates, like this zero rotation gates, non-fault-tolerantly. So basically, you do this zero rotation gates, but you do it like a with a leading order error p. So p is like the physical error rate. So you can see like because like the error rate they achieve is like a 2 to the 15 p. So this error is still quite large. It's not like a small error. But the good thing is like they can make this like a this constant, this like a 2 to the 15, this constant very slow, very small. Compared, I will not say very small, but it's still small. So in this case, they have shown like based on this like a hybrid partial fault-tolerant architecture, you can achieve like a like a reliable quantum computing with like several million Clifford gates and several 10,000 like rotation gates, arbitrary rotation gates. So this kind of like a hybrid quantum circuit can already like go beyond the capacity of the classical simulation. So this is like demonstrated in this paper. But the downside of this paper is that their like a rotation gate is non-fault-tolerant because the error rate is still like it's like a linear to the physical error rate. So so their capacity is quite limited. You cannot do many like useful applications. So our motivation is try to design like a hybrid fault-tolerant scheme where you perform a good you have a good Clifford gate based on lattice surgery or like a transversal gate, and then you have some like a moderate like a zero rotation gate. So I will mention later like we can construct some like a one fault-tolerant rotation gate where you can achieve like an arbitrary rotation with an error rate of p squared, or like for the small rotation, like where the phi angle is smaller than 0.2 radian. So when the phi angle is smaller, you can achieve like a logical error rate of phi p squared, where phi is like is a small value. So in this case, we can suppress the error rate to a very small number. So we propose a two scheme to like realize this like a zero rotation gate. Do you guys have any questions at this moment? Okay, so I will move on. So the focus of our work is try to design this kind of like a moderate, like a high precision rotation gate, one fault-tolerant zero rotation gate. So I will tell you how to design like this kind of rotation gate without any like a T gate compiling and like a magic state distillation. Okay. So before I move on to our like a core like a introduction of the error structure Taylor fault-tolerance, I will first briefly review the traditional gadget-based fault-tolerance. So the basic idea of like a fault-tolerant quantum computing is try to simulate like a ideal logical circuit like this one, like 2-qubit like logical circuit with a noisy circuit. So this noisy circuit, you have like a noisy state preparation, noisy gate implementation, noisy error correction, and a noisy logical measurement. So you want the output of the noisy circuit to be very close to the ideal circuit. To this end, so usually what people do is like to decompose this noisy circuit to many blocks. So for each like a red blocks, red like a rectangulars, like this dashed box, and or green dash box. So this box are some components of this noisy fault-tolerant circuit. So suppose as long as so the QEC can like sorry, this is correct. This is a typo. So suppose QEC can correct T errors. So when we have this like a noisy circuit, and for each box, the error number in each box is smaller than T. We recall that T is the like a correctable error of the quantum error correction code. Then we can safely say that this noisy circuit can simulate the ideal circuit faithfully with a very small error rate. So the basic idea is like we replace like each like a dashed like a noisy box to some ideal box, like gradually. And in this way, we can reduce this noisy circuit like to the ideal circuit, like a with a like still like a small error rate. So I guess like this is like quite familiar to like a Minshu, like to like the expert in this field. But I just want to like say something about it. Yeah. So
So there is sorry. So there is this recent paper by Sunny. So he actually gave a talk in our group meeting last week. Sunny He from MIT. They have this new idea of composable, like fault-tolerant idea. Is it similar to that?
Yeah, this is like a very old story, like a composable error analysis. I don't know whether what's new in the last week's talk, but this this kind of fault-tolerant idea is it's demonstrated 20 years ago.
Okay.
So this is the canonical. So what I want to say is some canonical gadget-based fault-tolerance analysis. So basically, for each box, you will have a fault-tolerant gadgets. And so for each fault-tolerant gadgets, for each small fault-tolerant gadgets, you can replace it to the ideal gadgets with a small error weight. And then gradually you can do this composable error analysis.
Okay.
So I don't know what is new
see.
in the last days, the last week's talk.
No, I think they just make all the definition more precise, and yeah, they define a lot of it's a huge paper. I also did not manage to finish it, but they defined a lot of gadget with formal definitions, and then analyze. I think based on similar to what you said, but I cannot tell which one is new and which one is not. Yeah.
Okay.
Yeah.
Definitely that will be interesting, but I think formally. So maybe I need to check the paper to see what's new. But yeah,
I think the main thing that at least they're selling that's new is so as you said, that there's a way to compose these gadgets, but their main goal is to do it in a way where you can actually get proper threshold theorems from it.
Okay.
Yeah.
Okay.
At least, but of course, I don't know at what extent things have been known before and which is the innovation.
This is a good point. So formally, this gadget-based fault-tolerance is used to prove the threshold theorem in the kinetic code, in the Niels paper or Danny Gottesman's paper. So they also demonstrate if you use a concatenated string codes or some even a better codes, how when you do the code concatenation, how can you prove there exists a threshold? So this composable analysis is formally is originally used for that purpose. So I don't know, maybe there's something new in the code construction in the paper you mentioned. But anyway, this is not the thing I want to claim for our paper. So I will this is just the background. Okay. So the thing I want to still I want to say some one more slides about the former old story. So usually people to construct this this box, this gadgets. So usually the way to do it is people use to introduce some fault-tolerant gadgets. So fault-tolerant gadgets is based on some ideal definition of the filter and the decoder. I guess you have seen these similar things maybe in the last week's talk. So I don't want to mention too much. So basically, the filter is like a projector, which is to project the Hilbert space, which is at most r Paulis away from the code space. So this is a mathematical object which you don't need to implement in the experiments. And the ideal decoder is a noiseless QEC. So when the error is correctable, the ideal decoder will recover the state to the ideal code state. So these are two objects. And with these two objects, you can define a fault-tolerant state preparation, gates, error corrections, and the logical measurements. So here I will take the gates as an example. So basically, a fault-tolerant gate is defined by these two definitions. So the first one is suppose you have R errors, at most R errors input, and there are S errors happens in the circuit. And when the number of these errors is smaller than the correctable error T, then the output error will be smaller than R plus S. So basically, the error will not propagate. So of course, this is just for the gate for one block. You have a definition for two blocks. So this is just for simplification. Okay, so basically the first requirement is to say the gate will not spread the error. The second requirement is when the error number, including the input error and the error occurs in the middle, is smaller than some correctable error, then the gate will functions very close to an ideal unitary, which is the ideal unitary you want to implement. So suppose you have these two requirements for the fault-tolerant gate. And also you have like similar requirements for the fault-tolerant state preparation measurements and the error corrections, then you can do this like reductions. So this is like the major idea of the former like error fault-tolerant error analysis. Okay, so now I want to say something like a new, maybe or something like I want to emphasize in our paper. So in their error model, so they consider these S errors. What's the meaning of these S errors? Usually people will consider an error model as like a local stochastic Pauli error model. So basically, let's see there's a very simple circuit with 5 gates and 3 Hadamard, C naught, idling, C naught. So this is a very simple circuit. So usually people will set the error model to be like after this Hadamard gates, you will randomly sample Pauli X, Y, Z like errors on this like after this gate. And after that, you have like let's see for this C naught gates, this is a 2-qubit gate. So you will randomly sample like a 2-qubit Pauli channels after this like a C naught gates. So basically you uniformly sample like a IX, IY, IZ, XI, XS. This 15 Pauli like terms for this like a Pauli error, depolarizing Pauli errors. So usually people will consider this like a stochastic Pauli error model, basically for their like for the simplicity for theoretical like analysis, and also this is somehow the worst case analysis because every Pauli errors will happens like with like evenly distributed, the uniformly distributed like probabilities. But this is like this may not be the like the errors happens in the experiments. So what is the errors happens in the experiments? Oh, sorry. So yeah, I just mentioned like this fault here is like a discrete on discrete locations. So the errors happens on what actually happens when you implement a gate. Let's see like a logical the Hadamard gate or a Sinar gate. So usually people will apply a drive, a Hamiltonian drive on the qubit. And during this Hamiltonian drive, so there will be some like a dissipation. The dissipation is basically like some like a Markovian, like a open system, like a Markovian dissipative procedures. So let's see like usually people will say like there's some like sorry this so this J will be like a relaxation or dephasing or like an excitation. So this J operator. So basically the dynamics of this like a gate evolution will be a continuous like dynamics. And the errors happens during this like continuous evolution. Well, these errors will happens at any locations during this like a continuous dynamic process. So this like a whole process, like under the Markovian approximation, can be described by this like Lindbladian mass equation. So here, like HT is like the drive of the Hamiltonian. Basically, the thing you want to apply, like the Hadamard gate. For the Hadamard gate, is like a x plus z drive. For the CZ gate, it's a ZZ drive, something like this. And this part is like some noisy, like some noise. So I don't know whether you guys are familiar with these things, but yeah. So maybe I can move on quickly because there are still too many like contents in our later discussion. So our consideration is that we are thinking about the driving. We're considering the case where the drive is much higher than the noise. So the noise is
Okay, so I just wanted to ask now. So in this picture, so what would it take for it to represent the local stochastic noise?
so I want to emphasize like the error here is still local.
Okay,
So
okay.
so like because the major reason is like the jump operator only acts. So this J operator, this acts on like some decay or excitation. This kind of like jump operator still acts locally on a single qubit or on some like 2 qubits. Let's say you have like 1,000 qubit devices, like a 1,000 qubit device. So when you only implement like the Hammer gate on like one qubit or two qubits, so these errors will only occurs still like occurs independently on different qubits.
Okay.
Okay. The major difference is that it's a continuous error. So which is like the real physical process. It's not like a simplified model where you apply a channel after the gate. Okay.
Right.
So usually people, so what we're thinking is like actually like in the former so these two papers are like some bosonic codes paper. So in this like bosonic error correction community, they have already considered similar ideas. That is to expand this error, like to the jump, the dissipation error to different orders. For the zeroth order case, you don't have any error. So this is the ideal evolution. For the first order expansion, you have one jump. I will call it jump, but you will also have these back actions. Well, the first order errors happens during this unitary evolutions. And for the second order expansion, you have two errors occurred during this unitary evolutions. You can expand this like a dynamical evolution to a very high order. Yeah, and so the basic idea is like in our analysis is try to use this expansion to replace the counting of the Pauli errors, like the counting of the number of Pauli errors. So let me try to clarify this. So we define we modify this like a fault-tolerant gadgets definition. So now we have like a very similar figures similar to the like former discussions. Now we define like a fault-tolerant gate. Like we call it error structure tailored fault-tolerant gates. So this fault-tolerant gate will satisfy these two requirements. So the first requirement is like when the code passes when the input error is past the R filters, and during this like a dynamical procedures, the dynamics is truncated to the S order, which means like at most there are S errors happens during the continuous dynamical evolutions. This this output state can pass this R plus S filter. So you can see like this definition is quite similar to the former one. So basically it's the same, right? But the only difference is that I changed the definition of this S by counting the number of Pauli errors in the circuit to the Dyson series expansion of the perturbative expansion to the continuous a dynamical procedure. But following this definition, we can just slightly modify this definition. We can still define a similar fault-tolerant gate definition. So if we can find some gates which satisfy this this new fault-tolerant definition, we can also say this one is fault-tolerant because this can also satisfy our requirements. This can also satisfy our requirements of this composable error analysis. So we can later show like the error rate is still you can also still write this a final error rate to some p to the t plus 1, this type of error rate. So it's still composable. Do you guys have any questions? So I know
okay.
it's not.
I'm just trying to think now. So how do you? So the counting now will be depending on this. So when you say that you have two errors, then it's sort of in this expansion you have this two second order.
Yeah, two locations. Okay. You have this the D errors, kind of jumping with back propagation. This is D errors.
Okay. And okay, so but this is in some sense this is more general, right, than the previous way.
Yes.
So yes. It will reduce to the Pauli error counting in how? How would it reduce? If the
yeah, this is a good question. So of course you can try to commute this type of D errors to the end of the circuit.
Okay.
Yeah, of course. But yeah, just the thing is in this case, I will show later of course you can expand every error of in the Pauli basis. You can write this chi matrix of this error channel. So the Ki matrix is basically like a Pauli expansion of the errors.
Mhm.
Right? But the errors is unnecessarily to be a worst case, like a depolarizing error. And so we will take advantage of this like observation, like experimentally. When you design this Hamiltonian to some specific Hamiltonian control sequence, the error is unnecessarily to be like a depolarizing error.
I see. Okay.
Okay. And I think like this is like we're trying to like taking the advantage of like the error structure in the experimental platform, not just like based on our like theoretical modeling, because like theoretical modeling is like sometimes like abstract, which is like far away from the real experiment. Okay. Okay, now let's move on. So, and another thing I want to mention is like I want to also mention like the error structure tailored for tolerance for QED code, quantum error detection code, because like actually we only like provide examples for the QED code with the for tolerance. So I will clarify it later how we use QED to prepare some resource state, and then we pro with like this can only the state can only be prepared like with a probability. But later on, we then use this like a resource state to inject it to the normal circuit. So this spirit is still like very similar to like a magic state cultivation or distillation. So you first prepare some resource state using some QED codes. So I will mention like also slightly like modify this like a definition. So for the QED code, the major difference is that the ideal decoder is not error correction anymore. So this ideal decoder will become like a projection to the code space. So if it fails, we will not perform error correction. We will just discard this run. Okay, so this is like the ideal decoder for the QED code. And we can also like define like this kind of like a for tolerance gadgets for the quantum error detection code. Basically, it's like it's basically like the definition is very similar. The major two change is like the decoder. Here, the ideal decoder becomes like a probabilistic projection to the code space. So here it's not equal; it's like proportional to. So because like we will lose some like we will like discard some components when like it cannot pass this like post selection. Okay. So now I have like discussed like we can like generalize this for tolerance, but how can we construct some example of this kind of error structure tailored for tolerance? So now let me give you some like a very simple example based on this like a 4112 subsystem code. So to explain what is like a 4112 subsystem code, I will first introduce like this like a 422 code. So which is like the smallest Tori code. So basically you have 4 data qubits, D0, D1, D2, D3, and I will like write it like following this notation, D0, D1, D2, D3, this 2x2 notation. And for these 4 qubits, you will have 2 stabilizers, 4x and 4z. Okay. And with these two stabilizers, you will have 2 logical qubits. The first one is given by this logical x and logical z. And the second logical operator is given by this gx and gz. Okay. And now we try to choose one of the logical operator to be the real logical operator, and we choose this like a second logical operator as some like a gauge. We call it gauge because we don't care about the logical information on this like a gauge operator. So in this case, we will get this like a 4112 subsystem code. So this one indicates the logical operator, the real logical qubits. So this one indicates the gauge qubits. Okay. I don't know whether I need to waste time here, but I think so. Basically, this like if you guys are familiar with like the Bacon-Shor code, so this is like the smallest error detection version of the Bacon-Shor code. Okay, now let's move on. So with this code, so why I want to use this code? The major advantage of this code is that you can do the state preparation, the logical plus state preparation very easily, using no measurements using just two Bell state preparation, and you have like one fault-tolerant, like a state preparation to prepare the logical plus state. And also you can do the quantum error detection. So this is like an error detection code because it's distance d. The d equals to 2. You cannot correct any error, but you can detect one error. So for this code, you can do the quantum error detection with only weight 2 measurements and no weight 4 measurements. Okay, so I don't know whether I need to it's quite technical, but I think you guys can check the paper for like a more detailed discussion. But the major idea is like this code is a distance 2 code. So logical z operator, this is like a d0 d2 z0 z2. So this is like a z logical z weight 2 z operator. Just remember this fact. And the two good things for this code is like you can do the state preparation and the quantum error detection in a very resource efficient way. Okay, now I want to say something about this code. So suppose you want to do some logical rotation gates under this like 4112 code. How can you do that? Here I want to say, suppose you want, of course, if you follow this like a Eastin-Knill theorem, it will tell you like you cannot do this gate like transversally. And if you want to do this like a T-gate distillation, this will be very challenging to do some rotation gates on this like a 4112 code. But now we want to claim, what we want to claim is like, if you do this like zero rotation gates by a Hamiltonian, very simple Hamiltonian, Z0, Z2. So this Hamiltonian can be easily realized in the real experiment, either in the neutral atom platform or the like a superconducting platform. You can do this like an interaction, like based on some dispersive interaction, dispersive Hamiltonian. Okay, so suppose you do this like this. Do I need to so let's see. If you do this like a Hamiltonian evolution for time t, then you can achieve like a rotation phi angle. Phi equals to chi times t. So you can realize the rotation gate. If you do this like a analysis based on some canonical like a fault-tolerant analysis, this like a rotation is definitely non-transversal, so it cannot be fault-tolerant. But now in our analysis, we are based on some like a Markovian like a discontinuous analysis. We have shown like suppose the error is described by some continuous errors like so relaxation and dephasing and excitation. During this procedure, we can show this gate, this non-transversal gate, is actually one fault-tolerant, based on our new definition of the like error structure tailored fault-tolerance. Okay, so we have some proof, but I don't want to say the details here. Do you guys have any questions? Yeah, the major message I want to say is that this non-transversal Hamiltonian base gate can be one fault-tolerant if you take the real error procedure into account. This gate can be one fault-tolerant. Okay. But sometimes like the experimental people will tell me like, okay, this gate is good, but I don't want to introduce like a direct coupling between these two data qubits. So this Hamiltonian is it's not achievable, because like these two data qubits are not close to each other. So how can we do this like a z rotation? So for this proposed, we also propose another way to do this like z rotation gate with like a ancilla. So basically you couple this ancilla to these two data qubits, and you do this rotation gate on this ancilla by a X drive, and you then measure this ancilla. And if you measure this ancilla and you get the right outcome, then you perform a ZZ rotation on these two data qubits. So we have also shown like for this like a Hamiltonian for this like a specific like Hamiltonian like a drive procedure. Basically, this CZ gate is done by this ZZ interaction Hamiltonian. So if you check this like a dynamical procedure of this like a Lindbladian like a noisy process, you can also get this you can also have this like a rigorous proof to show that this like the ZZ rotation gate is also like a fault-tolerant. So the basic idea is also quite simple. Like let's see, like do you have Jiao? I don't know whether you have any questions. Maybe it's like not very like mathematical. Yeah.
No, not yet. I don't know if anyone else has some questions. I guess like my what I had in mind is sort of just like, so when you like do this with an ancilla, then in some sense like the analysis will be different, right? Because you're really describing things at the level of the noise that you're encountering. So like then you have to show separately, right? So results without ancilla doesn't imply the results with ancilla, right?
So let's see, like so what we do is like we treat this like a whole quantum circuit as like a 5-stage Hamiltonian controlling procedure. So basically, for this stage, you apply a Y drive. For this stage, you apply 2 like a ZZ coupling Hamiltonian. And for this for this drive, you apply an X drive. And during each procedure, for these 3 qubits for this 3 like a system, there will be like jump operators like relaxation, dephasing, and excitation. These errors can happen during this whole like a dynamical procedure. And what we need to account is like for after this all errors, and also with the measurement errors, and what is the like whether it can be fault-tolerant based on of like a formal definition up to the first order expansion. Okay. So basically, the basic idea here is like it's a bit complicated, but let's say for simplicity, you think like we can think like some like a circuit errors happens during these procedures. Let's say suppose you have zeros here. Let me try to use some like a note like a laser pointers or pen. Maybe pen is better. So suppose you have a 0 here, right? And these zeros will not propagate, right? So the errors commute with this like a CZ operations. So this will commute, and so this will be just a zeros. Zeros happens at the end of the circuit, and the single zeros can be captured by these like error detections. Suppose you have an X error here. So the X error will propagate to an XZ errors. So this is a weight 2 errors. And you can show like this like a Z error. This is like a the propagated Z errors can also be detected. XZ errors can also be detected by this like by this ancillary qubits. Yeah, you can just like by counting these jumps, also or like for simplicity by counting these Pauli operators, you can check each like the first order errors, and then you can show like either the harmful errors will not ever happens, or the errors can be detected by this like a 4112 code, all these ancillary qubits. Okay, I agree. Like this is like a quite like a it's not like very clear explanation, but yeah, the basic idea I want to show I want to show here is like you can consider the the Hamiltonian procedure of this like gates instead of the circuit itself. So in this case, you by taking this the concrete like a dissipative error in the experiment, this will gives you like a more advantage, more like flexibility to design like photon gates. So just let me try to first clear my like my note all the thing here. Okay, and so just like for the simple case, like for this like 412 code, without this like Hamiltonian based analysis, you will never have a chance to design this like a rotation gate. That's simply based on this like without any like a T-gate compilation and any like a more complicated circuits. But now we only have this like very simple like a ZZ coupling, and this can be fault-tolerant. Okay. Now I want to say I want to show you some like a numerical simulation. Another thing I want to add a remark is that you can also replace this like ancillary qubits, GEF ancillary qubits to some like a dual real type like qubits. Anyway, this is like some details. I don't want to say something too much at this point. So we also perform some numerical tests, just like here to show like our circuit, our gate is actually one fault-tolerant. So this is like 412 code. We perform some like a numerical test, and the target is to prepare like this rotation state. Basically, you apply this logical rotation gate on the logical plus state, and you want to prepare the state, and you want to make this like a preparation procedure to be one fault-tolerant. So if our analysis here, like this proposition, is true, which means like this gate is actually one fault-tolerant. So in the numerics, you can see like the rotation gates can have a very high accuracy. Okay, so we just run this like a numerical circuit, and we use QTIP and QSK to run this like a fully coherent, like a dynamic procedure of this process, and we have shown like under like a reasonable experimental parameters, and also under this like under under practical noise model, in the based on like the superconducting like qubits, we can see like the errors can actually be suppressed to the second order. So X here is actually P. Like you can suppress the error to the second order, and of course like yeah, so the simplest like a ZZ coupling based like the gates will have a even smaller error comparing to the ancillary based, the more complicated ZZ rotating gates. So this red line is like the rotation, is the ancillary based ZZ rotating gates. The blue line here is like the ancillary free case. So based on these numerics, we have actually shown like you can do this like arbitrary rotation for one fault-tolerantly without any like a T-gate compiling and also matches the distillation. You just do simple gates, and based on this like practical noise, like practical experimental noise like a procedure, you can suppress the noise to the second order. Okay, now I want to see how you can use this like one fault-tolerant like a rotation design to the surface code. So how can we do this like so surface code is basically like the major like a code we are interested about in the near term, like error correction applications, and so we want to like implement a logical rotation gate on the surface code. Okay. So now so for the surface code, how can we perform a rotation gate? We propose two methods. The first one is called the expansion scheme, where you expand this code from the 412 code, like gradually to a large surface code. So basically, so this part is like a 412 rotation state preparation, and then you expand this code to a distance d equals to 3 surface code, and you repeat the measurement 3 times to the post selection, and if the state passes the post selection, then you expand it to a very large surface code. And in this case, you can prepare a R5, this is like a rotation state on this like surface code, and you then use this like a rotation state to implement a rotation gate in this way. So basically, suppose you have prepared a rotation state, and this is the system you want to prepare. You want to do like a rotation gate. You can do a gate teleportation. You inject this like a rotation to this like a psi prime state. Suppose that you do this measurement and you get the outcome 0. You can implement like a phi rotation the side state. And suppose you, on the other hand, if you get the outcome 1, you apply a -phi rotation on the side prime state. So in this case, I don't know whether you guys have any questions. Yeah, maybe I take too long time, and I will try to speed up quickly. Okay. So basically, you can do this rotation state injection, and you can as long as you can prepare the resource state on the surface code, then you can implement the rotation gates. Okay, and we propose a way to do this expansion based on this 412 code, and then we show like for this expansion, you can prepare like a rotation state on the surface code with a moderate error. I will not say small, but it's below 10 to the -4. It's like a small errors, but it's still not very satisfied. But it's like you can see like it's like a second order scaling. And this error is like so the rotation state is like a 10 to the -4 error. We want to like suppress the error to even lower. So this will, so to this for this purpose, we propose another scheme called projection scheme. Here we take some idea from this 2 papers by Choice and like Toshio for these 2 papers, where they implement some like this is a very long story, but I want to say it like simply. But basically, the basic idea is like you perform some like a small rotation gate on the surface code first, and then you do the code projection to like project the rotation state to the code space, and if the code if the projection is success, then you can actually like realize like a rotation gate. Basically, it's a way to combine a small rotation, which is like a non-logical operation, to a large rotation operation based on this code projection, based on the code projection. And so with this like Bayesian error suppression, you can suppress the error to this to 5p. Basically, the formally I don't know how to say it like very simply, but formally this, maybe I've prepared the slides for like 2 hours, so I will try to like explain it as quick as possible. But based on this projection scheme, what we can do is like we can combine with our like first order one fault-tolerant like ZZ rotation design. We can suppress the error to the 5p square, where phi is the like the small angle you prepare. And for the projection scheme, you don't need to like start from the 412 code, but you do some like you simply do some like a syndrome instruction on the very large surface code, and you do some rotation gates in the middle, and you do the projections, and if the projections succeed, then you successfully prepare the rotation state. Okay, and we also numerically demonstrate the projection scheme, and we show that, for example, for d equals to 6 rotating surface code, we have shown like for the projection scheme, you can prepare a rotation state with a trace distance, like basically the error, to 10 to the -8, to a very low error, when the phi angle is like 10 to the -3. So the error in this case, the error of the rotation state is proportional to 5p squared. Well, here I take p equals to 10 to the -3, which is like the physical error. P is the physical error. P is like a 10 to the -3, which is like the real like a hardware error, and the phi is like a small angle. I take it to 10 to the -3. So 5p squared is 10 to the -9, and here the constant here is like a 9.78. So basically, so the final rotation state you prepared is like is with a very high accuracy to like a close to 10 to the -8. And then we also show like you can by extending this like code distance, so the performance of our scheme can still be very reasonable. Like you can keep like the error weight of the like c times phi p square, the c values to be like a value around 10 or like 14. So 14 times phi p square is still a very small value of the error when you prepare like this rotation state. And we also show like how to like boost the successful probability to prepare this like a rotation state. And we have shown like for a d to the 18 surface code, you can prepare the rotation state with 5% successful probability. So this is like quite high. And so I want to skip some of the like discussion, and I will show you the conclusion in our resource estimation. Maybe this is just too long, and just after we consider all the error mitigation cost and like incoherent error, like a coherent error contribution, and some like repeat until success injection, and some like many factors, we can finally show like basically how many gates you can implement based on our methods. So our conclusion is that as long as in the Clifford plus phi architecture, as long as all the phi angles, so you have, let's say you have many phi rotation gates during this circuit. As long as this phi rotation angles is smaller than 10 to the minus 5 radian, then you can use our methods to achieve like a very low spacetime overhead, like a fault-tolerant quantum circuit implementation. So what's the meaning of this one? Like 10 to the 5 radian. So if you consider to implement like a Hamiltonian simulation with like a 100 spin on the Heisenberg model, so our gate design allows you to implement a Hamiltonian simulation up to like up to 300 like a time after of a time of 300. So this is like far enough for the near-term applications. Also compare. So this is like the capacity of our so this is like how many gates can we implement using our like a rotation scheme. So I also want to discuss about like the space-time cost of our scheme. So we compare like our cost to like the magistrate distillation and the magistrate cultivation, and we show like in the first order Chorter simulation of the Heisenberg Hamiltonian, if we use our methods to do this like a rotation list directly, instead of do this like a T-gate compiling, you can save the non-Clifford spacetime cost by like a 1000 times comparing to the magistrate distillation, and like a 50 times, 40 times, like a resource save the spacetime by a factor of 40 times using our methods comparing to the magistrate cultivation. So one important message here is like if we use our methods to perform a rotation gate, so the cost of our rotation gate is very close to a large surgery signal gates. What's the meaning is like in the near-term application, if you use our methods, then you don't need to take this rotation gate as a very resource-consuming object. You can just take it as a signal gate. So the space-time cost is comparable. So you don't need to worry about like the space cost of the rotation of the non-Clifford gates anymore in the like in the near-term applications. Just to summarize, so we designed some like hardware-based fault-tolerance, and this hardware-based fault-tolerance can help to improve the fault-tolerant design, and we show like how can you perform like a p-square perform like a second order suppression, first order suppression of the gating infidelity for arbitrary angles, and for small angles you can suppress the gating infidelity to a 5p square, and we can achieve like a very small like a 9 times 5p square like a error rate. And our methods is without any T-gate synthesis with a very small footprint and very fast. and we only requires like a nearest neighbor interaction, which is readily implementable on any superconducting devices. And this is my talk today.
All right. Thank you very much for this very illuminating talk. Yeah, I guess we kind of gone over the time. So maybe just like some quick question from the audience or some comments.
So now, so in our group, Kason and Kevin, the two of them, they are now thinking of using to integrate error corrections into quantum simulation scheme. I think I mean you did quantum simulations back then before working on error corrections.
This is actually kind of like a motivation of like doing this
Yeah,
work.
yeah, I know, because you use a lot of characterization as an example. So I would like to request Kason and Kevin to organize discussion with you, because
of course,
that is our next year's plan to in the quantum simulation is really to integrate error correction into the quantum simulation pipelines and at least did some like resource estimations and creating better gadget, more efficient gadget for quantum simulation. So Kason,你记得跟那个郑培老师约一下，好不好
Okay. Yeah.
Okay, good.
We already look into the star architecture.
Yes.
Yeah.
Somehow
But
we
we
are
are not-
following this star architecture, but I just don't like this terminology because like formally like in many old papers they also like mention this Clifford plus phi architecture. So we just don't use this name. Yeah, it's like we're kind of following this like architecture. So I know like recently they also have a paper to show how to like a resource estimation in the for the total simulation in the star architecture. They have like a PRX quantum paper this year. Yeah, but we can of course we can do better because like if you because using our using our methods, as you can see, like we can do like a just under the error rate of 1.10, just like this is like a very reasonable error rate, like a 10 to the minus 3 depolarizing under this error rate. We can actually implement like a very long time evolution, which is impossible in their case. So usually they do resource estimation, they assume like the p is 10 to the minus 4, which is something like far beyond like the capacity of the current devices. Okay, and yeah, actually we have done some like some very rough like resource estimation recently, but we can discuss. Like I want to see also, I want to know like what you guys I want to do.